let's say we wanted to find a vector that's perpendicular to both vector A and vector B. What would that first of all look like? Well, this picture, by the way, is in 3D. So if I, imagine drawing in like a little coordinate system, right? It would look, something like this, right? So these are vectors in space, and they're like if my fingers were the vectors, they're like kind of angled out, so they're kind of pointing out of the page. Well, the vector that's perpendicular to both of them would look something like this, right? It would be pointed kind of in the z direction, where it's perpendicular to both A and B. I can call this C. Now you can actually use dot products, and you can figure out a possible solution to this, right? Like, you can, obviously there would be an infinite amount of vectors, because you could have vectors that are really small, some in really big magnitude, some of them pointing down, but you can find a solution by setting A dot C equal to 0, and then B dot C equal to 0. And essentially you would have assuming these have components like A1, A2, A3 for X, Y, Z, and so on, A1 times C1 plus A2 times C2 plus A3 times C3 would end up equaling 0, because remember, for a dot product, we're taking the components, we're multiplying them, and then we're summing up the products of each of like the two components multiplied. So B1 C1 plus B2 C2 plus B3 C3 would equal 0. Now, that's you could solve this, right? This is a solvable system, and I'm not going to go through it just because algebra is a little heavy, but you essentially get one solution. If you one possible solution to solving this is a vector C1, or vector C, sorry, that is equal to, oh boy, let me actually give myself more space. A vector C will end up equaling, it will end up equaling something like A1, no, wait. It would end up equaling A2 B3 minus A3 B2, comma, it would end up then equaling B1 A, I think B1 A, I'm kind of going off my head here, B1 A3 minus B3 A1, comma, let's do, and then it would be A2 A3 or B3 minus A3 B2. Let me just check the book, just make sure that's right. A1 or, oh, that's definitely not right. That's definitely not right. What am I doing? This should be 1 and this should be 1. Well, you'll see in a second what I'm trying to do. This isn't even right. It's supposed to be like this. A1 B2 A2 B1. Is that right though? A3. Yup, that looks right. And that looks right. Okay, point is, if you solve the solution, you'll get this vector. And you could tell I was trying to memorize it. It's a pain in the butt to memorize, right? Like a vector that's perpendicular to both these things. So we worked with dot products, and now what we can do is we can actually multiply two vectors that actually gives us a vector result. And that vector result ends up being perpendicular to both these vectors or both the multiplied vectors in direction. And this is called the cross product. So C is actually really the result of A cross B. And that's like the notation. We use an actual cross, right? So in order to go about how to solve, or how to actually compute a cross product without memorizing this, to put it frankly, BS, you want to use determinants. So first things first, determinant, you might have done this if you go to the school that I go to, you might have done this in pre-calc. But if you had I don't know the exact terminology. Maybe I'll check the book. Sure, I'll check the book. Okay, it's not really saying. If you had a matrix that was like A, B, C, D, you could take the determinant by using the notation, like kind of like the magnitude notation, but it's not a magnitude. What I do is I do A times D minus B times C. This is how the determinant is defined. Why is it defined like that? Why is this a useful like definition? I don't know. I'm guessing it's a linear algebra thing, and I don't know linear algebra at all. But this is a determinant of order 2. I can take determinants of order 3. So I can say A1, or let's not even do that. How does the book do it? Yeah, let's just do it this way. A1, B1, or A1, A2, A3, B1, B2, B3, C1, C2, C3. This is not at all related to the vectors. This is just my own thing. Okay, new example. So to evaluate this determinant, what I do is I actually do. I have rice stuck here. Why do I have? That's really embarrassing and kind of nasty, but I swear I'm a not messy person. So I do A1 times the determinant to solve this. I do A1 times the determinant of B2, B3, C2, C3. Then I actually subtract A2, and I do B1, the determinant of B1, C3, and I believe these are called minors, and then, or B1, B3, C1, C3, plus A3, the determinant of B1, B2, C1, C2, B1, B2, C1, C2. So that's pretty cool. And these determinants I can solve pretty easily. I can say, well, this is the same thing as A1, B2, C3 minus B2, C3 minus B3, C2 minus A2, B1, C3 minus C1, B3 plus A3 A3 B1 or B1 C2 minus C1 B2. And the way I really determine like what am I taking the determinant of for A1? Well, I just take A1, I close out the like all the row and column and it's in, and then the remaining is what I'm taking the determinant of, right? For A2, it would be B1, B3, C1, C3. I cross out the row and column it's in. So this B2, B3 stuff, that looks kind of familiar. It looks kind of like this stuff, and that's because the cross product is actually defined by, so I can do it here. A cross B is really just a determinant. It's a determinant of vectors. I'm really doing the determinant of I hat, J hat, K hat. That gives us direction. And then I'm doing my A1, A2, A3, B1, B2, B3. This is actually how you can evaluate a cross product. Now, when I end up doing this, so when I end up doing this, I get A1. So if I'm going to do I hat times the determinant of A2, A3, B2, B3. I could write that, but I'm trying to save time. So I'm just going to evaluate that determinant in my head, but it's going to end up being A2, B3 minus A3, B2. Remember, I'm doing multiplying the diagonals and then subtracting by this diagonal. I'm using this definition of a determinant. And then I do minus J hat, don't forget that, minus J hat, A1, B3, right? I'm doing A1, B3. I'm not including this stuff, so I'm doing A1, B3 minus B1, or I'll just do what I was doing, A3, B1. Plus K hat, A1, B2 minus A2, B2, B1. And essentially, right, the I hat stuff gives me direction, so I can write this in more like a vector notation. This is really A2, B3 minus A3, B2, comma, the negative I distribute, so I get A3 B1 minus A1 B3, comma, A1 B2 minus minus A2 B1, and that's my vector. This is my cross product. This is C. So what you'll notice is, hey, yeah, this is the cross product. This is how the cross product's defined. Now, you know, this seems like a complicated process taking the determinant. And honestly, it kind of is. When you're first taking your cross products for the first time, you're gonna forget how to do it and like how to solve a determinant in the first place. You're gonna mix up the negative sign for the J term, and that comes from linear algebra. But with enough practice, this will just become like it'll feel like just multiplying 21 times 43, right? It becomes a habit. So don't fret too much about that. The main thing is just understanding how you do it. So let's just really quickly add just some other things. So one thing I forgot to touch on is if you had a vector A and B, and once again, it's like it is this is 3D. It's flared out a little bit out of the page. If I were to find the direction of, let's say, B cross A, right? Yeah, B cross A. Its direction, we know it's going to be perpendicular, but couldn't there be two directions? Couldn't it be this way or this way? That's true. So we've decided, as a scientific mathematics community has decided that the direction of a cross product is determined using the right-hand rule. Two ways to do it. Or actually, I'll just show you one. This way is just more simple. You take B and you curl your fingers in the direction to turn it towards A, and then your thumb gives you the direction of the cross product. So, boom, this would right here, right? If I use my right-hand rule, curling B towards A, my thumb points up, so I get B cross A. Hey, if I do A cross B, what do I get? Well, if I do that, I get I was about to say torque. I'm going to get a cross product that points this way. So what do I notice? Well, A cross B cannot equal B cross A because they're vectors, and these vectors are not equivalent. They're pointed in opposite directions. But what is the same about these two ends up being the magnitude. And a theorem that you can prove, I just won't prove because I don't know how useful people find proofs. And also, you can look it up. And also, if you guys really do want me to prove it, I can make a video more than happily. I just don't want to waste your time, honestly. You get that the magnitude ends up being magnitude A times magnitude B times sine theta, right? So this ends up being the magnitude. Now, that's pretty neat, right? This will, obviously end up being the same thing for both. And that gives us a new kind of, I think it's called a corollary, I don't know. You can solve for theta, right? And what you find is that, well, if your theta is 0, the magnitude is 0. And if theta is 0, that means they're parallel. So two parallel vectors will always have a cross product of 0. So if the cross product of two vectors is 0, that means the vectors are parallel. It's pretty useful, right? And down the line, for sure, it'll be useful. And this formula in general is useful. It's because, well, hey, let's say you have a parallelogram, right? Well, the parallelogram, let's say this is a vector A, and this is a vector B. I can find the area of this vector, or of this parallelogram, by taking the cross product, right, going through the determinants and the minors or whatnot, taking the cross product, and then taking the magnitude, because I know that there's going to be some angle theta, and I know the area is just going to equal A times B, the magnitude of B, sine theta, which I know is just the same as the cross product. I don't know why I drew it like that. I thought I was going to take an actual cross product there for a second. So, if I know those actual, you know, if I should I do an example? Let's do an example. Why not? So from my note sheet, let's say that these vertices, right? Let's say I have a parallelogram with vertice k, which is I'll do it like this, with the vertice k, which is 1, 2, 3. I have a vertice L, which is 1, 3, 6. I have a vertice M, that's 3, 8, 6, and I have a vertice N, which is 3, 7, 3. Well, this is a parallelogram in 3D space, which is kind of wonky to draw. So I'm not going to draw the exact coordinates, but I'm not even going to even try to draw the exact coordinates. But if I just draw a parallelogram anywhere, right? I know that, hey, you know, if this is K, this is L, this is going to be M, and this is going to be N. So I know that, well, hey, the area, right, will end up being this length times this length times sine theta. And that's a formula of a parallelogram. I probably should have clarified that. That's a formula for the area of a parallelogram. And I can just find the cross product of the vector KL cross KN. That take the magnitude, and that'll be the same as the area, right? Because it's going to end up, the magnitude will end up equaling KL, KN, sine theta, and that's just the area of a parallelogram. So the vector, so let's just get my determinant going. I guess I'll do this notation, right? Cross KN. I'm going to do my I, J, K. So from K to L, well, to go from K to L, wait, did I do this right? How on earth did I get that answer? How did I get this answer? K to L. All right, we're just gonna do it. We're just gonna do it this way, and we're gonna see if it gets the right answer. From K to L, I'm going 0 change in x, so that direction vector will be have an x component 0. I'm going 1 from 2 to 3, and then I'm changing my 3 from going to 3 to 6. Right? That's how I find the vector between that is starting at one point, ending at another. And then I can do the same thing from K to N, right? So I get basically, I don't know why I just lost train of thought. 2, there's no way this is right. 5, now that I'm thinking about it, 0, but you know what, we're gonna try anyways. So, we're gonna do our I hat, so 1 times 0 is 0, and then 5 times 3 is negative 15, plus, or I guess minus j. So then 0 times 0, and then minus 2 times 3 is negative 6, plus k hat, 0 times 5, and then plus 2 times 1, so 2 k hat, or minus 2 k hat. So I'm doing 0 times 5 minus 2 times 1. So now I get a vector, negative 15, 6, and then 2, negative 2. So to find the magnitude, so KL cross KN, I'm just using my magnitude formula. So square root 15 squared plus, or negative 15 squared, but it won't make a difference, plus 6 squared plus negative 2 squared. Oh, I do end up getting the same thing. That's cool how the math works out. I must have done different vectors or something. But 15 squared is 225, plus 6 squared, 36, plus 2 squared is 4. So 36 plus 4 is 40, 40 plus 225, that would end up equaling root 220, or root 265, which actually ends up being the area of this parallelogram, which I think is pretty cool. Like, we're given coordinates in 3D space. That would be really complicated to like do all my distance formula and then find the angle using a dot product. No, I can just take a cross product, take its magnitude, and I get the area, which I think is pretty sick. Genuinely, I genuinely think that's pretty sick. So, well, one thing I want to show you also, I guess I kind of pointed out, I kind of pointed this out, you know, cross product's not commutative. So if I do KL cross KN, this vector will have the same magnitude, but it'll end up being in the opposite direction if I do KN cross KL. So it's not a commutative thing, right? It's returning vectors. Like, this is not, you know, they're not the same vector just because they have the same magnitude. You got to think about direction. So just keep that in mind, right? Also, hey, you want to see something kind of crazy? Well, if I do I cross J, and these are my standard basis vectors, right? If I'm doing this, well, I cross J, let me just do that real quick. So I'm doing 1, 0, 0, 0, 1, 0, right? This is I hat, this is J hat. I end up getting, I'm just gonna skip the whole I, J, K stuff to save time, but I end up getting, for the X component, I get 0 times 0 times 0, that's just 0. You can actually probably think of like what this answer might be. I get J, so for the Y component, it's going to be negative, but I get 1 times 0 minus 0 times 0, that's 0. And then for the this component, I get 1 times 1 minus 0 times 0, that's just 1, right? This is actually just K hat, right? So if I, this is really just K hat. So if I now do I hat cross K hat, I get now, let's do the same thing. And you can once again think about what it's going to be. In fact, I'm not even going to evaluate it. We know it's going to have a magnitude of 1 because they're both, I is orthogonal to K because, you know, they're one is Z direction, one is X direction. So the magnitude is 1 times 1 times sine 90. Sine 90 is 1. The magnitude has to be 1. Well, what's a vector that is perpendicular to I cross J? That's going to be magnitude 1. Well, it's going to be J hat. Almost, it's going to be negative J hat. Because if I use right-hand rule, curling from I to K, it's going to be negative J hat. But you can also prove it with doing this whole thing. But now, if I do I hat cross J, right? If I change my parentheses using that associative property, I think, well, I hat cross I hat, that a vector is always parallel to itself, so this will actually end up equaling 0 because they are parallel. You can also go through the thing. You can imagine what will happen if I change it to 1. You think about it. So 0 cross J hat will be 0. So this is not a associative thing. The associative property won't always hold. But there are some other properties, which I want to show to you. I'm not going to go through all of them, but this is just a reminder that the properties don't always like transfer over from the scalar world. So here are the properties. This is me doing my notes. Yeah, there you go. So hopefully you took a screenshot, all that good stuff. One thing I want to talk about is a scalar triple product of vectors. So let's say you had 3 vectors. Let's say you have 3 vectors like this. So I have let's do it like this. So let's say this is A hat, right? Yeah, sure. A hat, let's say this is C, or not hat, sorry. A, C, B, right? So if I can do something called a scalar triple product where I take basically 2 vectors and I take the cross product and then I dot product it with the other vector. And this is called a scalar triple product, and it'll return a scalar, hopefully pretty intuitively. But what will this actually equal? Well, here's the deal, right? I know that B cross C will end up equaling my I, J, K hat times B1, B2, B3, and then my C1, C2, C3. And when I dot this with A hat, what am I doing? Well, I'm taking the A1 component, right? I'm taking the A1 component, so I guess this is really bad notation, but I'm taking my A1 component and I'm multiplying it by, well, when I take this vector, the x component is going to equal this determinant right here, right? That's really the that is the x component, right? Because when I'm doing my cross product, it's I hat times this determinant. Same thing, right? When I'm adding A2, this ends up being the y component ends up being the negative determinant of my B1, B3. So negative B1, B3, C1, C3. And same deal, A3, I'm multiplying, like this is what a dot product's doing. I hope that's kind of clear, right? This is the x component of B cross C, multiplying with the x component of A. So then it's A3 times K, the K component, or the Z component, which is B1, B2, C1, C2. And what do you notice? Well, what I'm doing right here, this whole process, this is the same exact thing as if I had just done A1, B1, or A1, A2, A3, B1, B2, B3, C1, C2, C3. If I took the determinant of all the components. So this is really equivalent to this. This is a pretty useful quantity because, well, if you think about it, let's say we just, I don't know, make a parallelepiped, which is like a 3D parallelogram basically, where you extend this, and then you extend this, and then you extend this, and then I can make this cool shape. How do I find the volume? Well, the volume's going to be, it's going to be the base times the height, right? So the base is going to be, so the area of the base is going to equal the magnitude of B cross C, because this is a parallelogram. And the height, well, the height is going to equal, if you think about this angle theta right here, so if I draw my height vector, or not a vector, I really shouldn't say, but if I draw this height, this is an angle theta, so this will end up being, let me just make sure my notes are good, yeah, so this will end up being the magnitude of A times cosine theta. Well, here's the deal, right? When I take B cross C, it will be a vector that's the same direction as like this quote unquote H vector. So if this is B cross C, then this is the angle, this angle theta is really just an angle between B cross C times A. So when I do area times height, I'm really doing B cross C, the magnitude of B cross C, times the magnitude of A cosine theta. This is a dot product, right? Because this is the angle in between them. So this is the same thing as A dot the vector B cross C. So the volume ends up being this scalar triple product, which is pretty cool. Now, that's actually how you can determine if three vectors are coplanar, right? Because if you end up taking this whole determinant, let me check on if I have enough time, I'll do an example. I don't want to drag this video. Yeah, 30 minutes is kind of pushing it. I'll make an example probably after this video or something. But if you take three vectors that are coplanar, right? If A was coplanar, meaning on the same plane as B and C, well, this volume would be 0. So when I take the scalar triple product, it would end up equaling 0. So if you're taking the scalar triple product of three vectors and you end up getting 0, that just means that the volume would end up equaling 0 of the parallelepiped, but that just means that the three vectors are on the same plane. So that's pretty useful. The last thing I really quickly want to talk about is torque. This is in the textbook, a cool little thing they do. So we know in physics, torque is like a quote-unquote twisting force. That's not really a force. It's how much rotational acceleration no, that's not a good way to put it. It's torque is a thing that causes rotational acceleration, and more torque will mean more rotational acceleration. Torque is just defined as the cross product of, so if I had like a door, right, it's defined as a cross product of this force vector and this displacement vector, right? So it's defined as this cross product. So if I do F cross the displacement vector R, I would get the magnitude, or I would get the torque vector, which would either point into the page or out of the page. And then I can find the magnitude by either doing magnitude of R cross F, but that just ends up being magnitude of R times the magnitude of F times theta, the angle in between. So this has been cross product. I just wanted to throw that in because it's a pretty cool connection to physics and why we use cross products, like why this is a useful thing to do. So thank you for watching. Hopefully this video didn't go too over your head, even though I did a lot of talking.